Okay, so how does k-means work, right? And what are we trying to do with it? So let's assume for the purpose of applying clustering, I have a data set that looks like this. Okay. Now so what do we do when we are doing clustering here, right? Like if this is my data set, what you see on my screen, let's say, right? Let's say this is my data set. This is a scatter plot of my data set. I am trying to understand the structure of my data set, and I'm trying to say that, hey, I can have about 3 clusters in this data set, right? Or 2 clusters or 4 clusters or whatever, right? That is the number k in your k-means, right? You supply this number explicitly to the method, to the model. You tell it that, hey, I want to see 2 clusters in my data, or 3 clusters, or 4 clusters, or 5 clusters, and so on. You supply this value to the model, and it tries to grow the specified number of clusters in the data set that you provided with, right? So for the purpose of this example, let's assume that there are 3, because visually when we see the scatter plot, right, we are able to see some 3 different groups of data. Okay, so for the purpose of this example, we will assume k is equals to 3, and we will proceed with the example. Let's say k equals to 3. Right now, how does the model grow 3 clusters from this data set? Okay, so the way it proceeds is in something called iterations. Okay, let's say in iteration 1, right, in the first step, what it does is it doesn't assume any of these points, okay, that are present. It just assumes that there are 3 points that are present at each point, at each stage. Okay, so it might pick this point here, it might pick this point over here, and it might pick this point over here. Okay, so these 3 points are picked up, and this point is called C1, centroid 1, C2, centroid 2, and C3, centroid 3. Now, how does it know to pick 3 points? It knows from our k value. If I mention 4 here, in the beginning, it will pick 4 points, 4 random points. If I mention 5, it will pick 5. If I mention 2, it will pick 2. Here, since I mentioned 3, it will pick 3 random points from your data set and call them centroid 1, centroid 2, centroid 3. This is my first iteration when I have 3 clusters of 1 element each. Okay, actually, let me mark these with different colors. Okay, my first cluster is light blue, my second cluster is magenta, and my third cluster is light pink. Okay, this is what it is. So this is my first iteration. I have 3. Forget that you are seeing the dark blue points on the back end. The reason why I have them is just to showcase that that's our entire data set. Okay, but focus on the 3 centroids that you see. So this is iteration 1. At the moment, it has 1 point each in each of these clusters. Cluster 1 has C1, which is labeled as 1. That's your centroid 1. Cluster 2 has C2. Cluster 3 has C3. These are the 3 centroids, and they're labeled as 1, 2, 3. 1 being light blue, 2 being magenta, and 3 being light pink. Now, let's proceed to iteration 2. In iteration 2, we will pick 1 new point, right? So let's pick this point over here. Okay, this point P1. Now, I will check the distance between P1 and C1, centroid 1, distance between point 1 and centroid 2, distance between point 1 and centroid 3, right? I will check all the 3 distances. This is let's say D1, D2, D3, and I see that D1 is the smallest amongst them, which means my point is closest to the centroid 1, in which case what I will do is erase these 3 lines. This is my point P1. So I will draw a line here. First, I will mark this as my point 1. So see, by marking, what the model basically does is it's labeling this point as something belonging to cluster 1. That's why I put the light blue color here. Okay. And then this is the distance. Then what I do is, if this is my distance, the point right in the center of it here, this becomes my new C1. Okay. C1 shifts to a midpoint of the 2 points in my cluster. Now this is the centroid 1, and these 2 points are my cluster 1. Cluster 2 is still 1 point, cluster 3 is still 1 point. Then moving on to iteration 3. Third iteration, what happens? Yet another point is picked up. Okay. Let's say I will pick this point now. Okay. Now again, same drill. How far is this point from centroid 2? From centroid 1, now centroid 1 has changed. So it will be distance between these 2 points. This black point here, this centroid 1, and this new point, point 2, let's say, and point centroid 3. Centroid 3 and centroid 2 have not shifted, so they'll still be the old ones, right? And I see clearly that it's closer to centroid 2. So I will take out the distances. I will mark this as with the color of the second cluster. I will recalculate my centroid to be the midpoint of the line joining these 2 points. Now, instead of centroid being this one, centroid will be this new midpoint. Okay. So now I have 2 points in cluster 1, 2 points in cluster 2, 1 point in cluster 3. Centroid 1 has moved, centroid 2 has moved, centroid 3 has remained the same. Okay. Now I'll move to cluster iteration 4. I'll pick another point. I'll add it again. So like this, I will keep adding points with every iteration. I will label them. I'll move the centroids, and this is how I'll grow my clusters. Okay. The only situation in which the algorithm will stop executing is either it runs out of points, new points to label, or the centroid stops moving very widely, right? The 2 points, the new point that is being classified might be pretty close, or the distance, right? It might shrink a lot, and then the centroid is no longer moving anywhere. That is the situation where the algorithm might stop. So whichever happens earlier, the algorithm will stop at that position. So more often than not, whenever you are performing clustering, you will always run out of new points to label, and that's when your algorithm will stop. Okay, you will never encounter the other case, because for that to happen, you need to have extremely large amount of points and very well-defined clusters as well at the same time. And all the 3 centroids or 4 centroids or whatever K, the number of clusters you're looking for, all the centroids should stop moving, and that's much more difficult. That convergence is much more difficult to happen, or rather it's going to happen very late, and it's something that you can see in a very large data set. The earlier thing that would happen is basically you'll be running out of points, new points to label. Okay, so this is how k-means works.
So to determine the number of k-means, you said, do we do that randomly, or you said to?
Correct. So there are a couple of methods, and that's what we will discuss right now, right? But you know how you understand how the k-means model itself works, right?
Yeah.
Cool. So now, what do you use to determine the optimal number of clusters? So you take a guess and run the model for 2 clusters, 3 clusters, 4 clusters, 5 clusters, or whatever, right? In our case, we looked at the scatter plot and we are saying that, okay, there may be 3 clusters. So I'm mentioning my k value as 3. But how do you know what's the optimal number of clusters? Let's say it's multidimensional and you can't build a scatter plot. How do you determine the optimal number of clusters? So there are better ways to do that. So there is one silhouette score or silhouette coefficient. The other one is my elbow method. You can use either. There is a third method. We will not discuss that at the moment, but it's a criterion called AIC by BIC. BIC is Bayesian information criterion and AIC is something else. So you take a ratio of these two metrics. It's a lengthier calculation, so that's why we did not, we are not covering it in this class, but I will provide you a link post our class to this AIC by BIC ratio, and you guys can like look at that and read up if you guys are interested. But the first two methods is sufficient to understand how to calculate the optimal number of clusters. Silhouette score is pretty straightforward. So silhouette score is pretty straightforward in the sense that it's a metric that is available in sklearn's metrics library, and you can straight away use it and determine what's the optimal number of clusters. Okay, so see this example in this is from your notebook, ML engineer's favorite, the k-means. Okay, so these are 5 groups of data that are created and labeled. Okay, so this is your k-means. Now what are silhouette scores? So this is the import statement, the first line that you guys see from sklearn.metrics import silhouette underscore score. That is the import statement. So once you import that, what do you do? On the blocks above here, you see that your k-means model has already been created. You have k-means, and the way you're doing it is from sklearn.cluster import k-means. K-means is equals to k-means, n clusters is equals to 5. This is the k value, right? N underscore clusters. Then you do k-means.fit, and then you give the data set. The data set is X, right? You supply all the data set, and then you have the k centers, labels, and this is a simple visualization that you are building. It's a seaborne visualization. It's a pair plot. Okay. So, and then it shows you these these clusters, okay, with their respective labels. Now, how do you use silhouette scores? You are creating 2 lists, right? So we have a k clusters list, then we have a silhouette coefficients list. For n cluster in range 2 to 11. So what we are doing is we are assuming that our k value starts from all the way from 2 and might go up to 10, right? So and for each of these n cluster values, we are redoing the code, right? So you see here, right? We are redoing the k-means algorithm with a new value of k each time, and we are fitting it to the same data set X. Once you fit, you get the labels. Once you get the labels, you calculate the silhouette score, and the way you calculate it is once you have this import statement, silhouette score, right? You do silhouette score, and then you give it your data set and label, right? Label is basically number of labels. So you are telling it, hey, this is my data set. And I'm assuming that for here, right, labels basically is 2 here, right? Because in my first iteration, I'm assuming that k value is 2. I'm trying to look for 2 clusters in my data set. So this label is going to be 2, number 2. And then this is my data set. And then I calculate the silhouette score for this data set. Okay. This data set, this many number of clusters. Right. And then what I do is I format it, I'm printing it, I'm appending the silhouette score and the number of clusters to both these lists. And why am I appending it to both these lists? Once I have the entire list built out, which means I am redoing my k-means algorithm for all values starting from 2 to 10, right? And I'm calculating silhouette score for each of these clusters. So for 2 clusters, what is my silhouette score? For 3, what is my silhouette score? For 4, for 5, and so on. So for each number, I'm calculating my silhouette score. And then what do I do? Number of clusters on x-axis, 2 all the way to 10, and silhouette scores on y-axis. Once I plot this, I see that my silhouette score peaks at 5, right, in this case. So at 2, it is somewhere here between 0.4 and 0.45 and 0.5. Then it climbs up a little bit here, goes slightly higher, then it goes even higher, then it goes ultimately at the max value, probably about 0.675 or something like that, right? Slightly higher, 0.68 maybe. Then it comes down even more, and so on. So like this, when you rerun the k-means model for various values of k and calculate Silhouette score for each at each k value and plot, you will get one peak, one distinct peak, which will tell you clearly what is the optimal number of clusters. Now, if you see here, I had 5 clusters, and visually also, when you look at this data, you can clearly see these 5 groups of data, right? So you clearly see 5 groups of data, and at the same time, your Silhouette score is also telling you that 5 is the optimal number of clusters that you can see in your data set. Okay, so this is how you use Silhouette score. Pretty straightforward, pretty simple. Just import the method, put your model inside a for loop, run it for various values of k and calculate Silhouette score for each value of k, plot it for the number of clusters on x-axis and Silhouette score, the coefficient that you get on a graph, and then wherever you peak, that is your optimal number of clusters. Now, how is Silhouette score itself is calculated? That's something that you guys don't need to understand and don't need to know, but think about it that it's kind of a error metric. So it's trying to reduce the distance between points in a cluster, and that's how it works. It's the same concept with elbow method as well, but the value is a little different. So we'll discuss elbow method next.
So the Silhouette score is just trying to let us know the number of cluster.
Yes, the optimal number of clusters.
Cluster.
Okay, because what happens is, as with these models, right, like they can create 2 clusters. Now see, for example, this same method, the same what do you call function? Actually, let me try and edit this notebook. I'll show you guys what I mean. Oh wow, not even logged in.
But the number of clusters is something that we actually give to the n cluster in k-means.
Correct. You give the number. So that's why what you're doing is you are guessing that number might be somewhere between 2 and 10. So in a trial and error fashion, you are running the model for all values between 2 and 10, and you're using Silhouette scores to determine what's the optimal number of clusters.
Oh, okay, I get it now. So you are trying to use the Silhouette score to determine the number of clusters you have to use.
Correct.
Okay.
Absolutely. So I'll show you guys what happens. So let's run the same code, right? Like that you see. Hopefully it works and everything runs cleanly. When it runs cleanly, what I want to do is I'll show you guys so you have the visualization in the notebook, which shows 5 clusters, right? I will do 2 clusters and you guys observe and see what happens when we do 2 clusters with the data, right? So we have these 5 clusters here. So again, this is just the data. We haven't yet performed the k-means. Now we will perform k-means. Okay, and we will visualize the data set. Okay, so you see here we have the k-means. Now, if you guys actually see this, right, like this is my original data set. Okay, how do you know that these 2 points pretty much look similar, right? Pretty much look the same. The only difference, the way you can tell the difference, and the reason why they are so similar, this real figure and the clustering is so good, so neat, is because why they both seem similar is because my clusters are so distinct, right? In this case, I'm using the make blob function. It's a function that creates these groups, right? And that's the reason why they are so neat. But how you can observe is, see these particular points. Okay, see these particular points here. So wait, annotate. I have 2 red here, 1 red here, and then 2 purple in between. Okay, now when I Clear all my drawings. Remember this, 2 on the bottom, 1 on top, 2 in the middle, right? That's the red and purple section. See here, right? Do you guys look at this part here? So this was red. This was also red. This middle point were purple. When it is labeling them, what is it doing? It's kind of like having a boundary like this somewhere in between, right? And it's saying all points on that side are yellow, on points on this side are purple. Now it doesn't have a boundary. How does it construct? How does it assign these labels? Do you guys remember? We just spoke about it in the earlier part of this class. Centroids, right? Picks a random point, creates centroid, adds a new point to it, colors that point, creates a new centroid, moves on. So what I'm trying to tell you is the model is guessing that these 2 points are yellow and these 3 points are purple, okay? But in the real data set, right, the red points are kind of overlapping here and the purple points are kind of like, overlapping like this, like they are crossing over. This kind of overlap is not there, right, in the k-means, because it assumes that these clusters are all close to each other. But reality is this is reality, that there is overlap. This is what the model assumes, that there is no overlap. Okay. Now, well, anyways, we saw this for 5 clusters. What happens if we do 3 clusters? You see that? Model still works. It grouped these 2 clusters as blue, this one as yellow, and these 2 as green. Okay. What happens if I do 2 clusters? See that? It's assuming these 2 are one cluster and this is. So the point is now, no matter what, see, visually here you can clearly say that these are 5 different blobs, but your real data might not be so distinct, right, that you can visualize it and see. So this is really the problem. Whatever number of k you give, let's say if I give 10, what happens? Whatever number you give, right, it will still work. It will still try to give you these many different number of labels and clusters. It will try to grow those clusters in such a fashion, but it really doesn't work well, right? It really doesn't know which one is the correct number of clusters. The only way you can do that is by using metrics like this. Silhouette score is one. Elbow method is another. So elbow method is what we will discuss next. Okay, it's pretty similar. For this, I'm kind of referring to Geeks. This is an article. I will provide you guys with this link. So here what happens is, in this code, right, in this particular page, you are doing all this, then building the clustering and calculating the values of distortion and inertia. That's something that they are saying. And then, okay, there's distortion, there's inertia, blah, 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 whatever calculations they did. And then they finally plotted this distortion versus values of k. They plot this particular thing, and you see how this looks like an elbow, right? It drops off at a certain value and then it kind of stays silent, right? In silhouette score, you're looking at a peak. In elbow, you're looking at the tip of the elbow. So if you think of this as a hand, right, you're looking at the tip where the forearm straightens up. So this point. So here it tells us that k equals to 3 is the optimal number of clusters. Okay. Now, what is this distortion? What's value of k? What exactly is going on here? Don't bother about distortion, inertia, and all those terms. I'll tell you the mechanism of how it actually works. Okay. So in elbow method, what happens is, in elbow method, what happens is, the way this is calculated. So as we saw, let's say I have all these data points, right? What exactly is elbow method calculating? So first, it assumes that there are only 2 clusters. Okay, so k equals to 2. First, it assumes k equals to 2. says, okay, this is one cluster, this is another cluster. Okay, let's assume that the model is thinking there are two clusters, k equals to 2. These are two of my clusters. What it does here is it checks the distance between all these points, right? Checks the distance between inter-cluster points, okay? And it averages them out. So it does the same with the other cluster, and then it averages them out, okay? And it comes up with a specific elbow score, with a particular score called the elbow score or whatever, right? The distortion, so to say. That's what is being plotted, right? So it's ultimately called the distortion, but that's basically what it is. It's looking for the distance, average distance between points within the cluster. So if it's two clusters, right, these are the distances. Now with observation, can you guys tell me average distances between this cluster and average distances between this other cluster? Can you guys tell me which is going to be higher? Is average distance is going to be more in the, let's say this is cluster 1, let's say this is cluster 2. Average distance here, right? Is average distance 1 going to be more or average distance 2 going to be more?
I think 2.
2, right? Why? Any justification?
Just like looking at it, it just seems like it's doing a lot.
Yeah,
Like,
it's longer, right?
yeah.
Exactly, right? It's doing a lot. It's combining two clusters into one. So what happens is there is this gap here, right? And there are actually two clusters in here. So these distances will actually grow, right? It's a lot of gap between these 2 points. So this ends up boosting the average distance up. Now what happens is on an again, average distance of first cluster, second cluster, this is for k equals to 2. It considers an average of all of these distances, and you'll have a high value because of these distances, these large distances. Then it picks up multiple, right? So it picks up 3, then k equals to 3, let's say. Next iteration, it assumes that there are 3 clusters. It will take this one cluster, this cluster, this cluster, right? Now I will get a some value of the distance. Let's say it's my medium value or so, right? Then I can supply 4 or 5 or whatever, right? So if I say 4, right, let's say these are 2 clusters here, 1 cluster, 3 cluster, 4th cluster, right? These are the 4 clusters. Then let's say if it's 5, right, this will be 1, 2 here, 3, 4 here, and then 5th cluster might be this one, right? In this case, what will happen? Again, distance might be short, right? Let's say lower than medium, right? But if you see this distance and this distance might not be too different, right? And that's exactly what elbow method does. Once you calculate and average it and plot these distances, this is k, 2, 3, 4, 5, and so on. For 2 clusters, the distance will be very high, somewhere here. For 3, it will be somewhere here. For 4, it will be here. For 5, it will be here. So you see a sharp decline, and then it will be slightly on the downward trend. It will keep decreasing. The more number of clusters you have, the smaller the distance, average distance number will be. But the dip will only happen once. And the moment the dip happens, that's where you determine that that's the optimal number of clusters.
Does that make the elbow method not a good one? Because why isn't it predicting 5 like the other one?
Oh no, here, because this is the data set that I took. In my data set here, it's only 3 clusters, right?
Okay.
And I drew it, right? I didn't program it.
Okay. Got it.
Right. Yeah. So if you do the elbow method, same elbow method in your notebook, right, you should get 5, right? So that's why in clustering, right, like it really doesn't matter much about which metric you pick, because you are going to get the same number, right? You should technically get the same number. If you're getting different numbers, then you'll have to, that means that there's a lot of overlap in your data, and that's why different metrics might be performing in a different way. But as long as you don't have too much overlap in your data and groups are pretty distinct in themselves, every method should give you the same number of optimal, what do you call, optimal clusters. But it's not the same in case of regression or classification, right? Let's say regression even more, right? There is MSE, there is R squared. MSE, you get a totally different number. MAE, you get a totally different number. R squared, you get a totally different number. If you use each different metrics, each different metric might give you different numbers, right? For the same models, right? If you use a MSE, you'll get different numbers for all the models, but again, comparative to each other. If you use R squared, you'll get percentage values, right? You'll get a value between 0 and 1, which kind of tells how accurate your model is, right? So that's basically how metrics are different. They might yield different values in regression, but in clustering, as long as your clusters are like pretty well defined and have less overlap, every metric that you use, even AIC by BIC, should still say 3 is the optimal number of clusters. In this case, in your notebook, if you apply AIC by BIC, it should say 5 is the optimal number of clusters. Okay, so every metric will give you the same value. It doesn't matter which one you use. You can use Silhouette score, you can use AIC by BIC, you can use elbow method, you can use whichever you're comfortable with.
So before, like, you do the K means, you have to first do the matrix, so that way you can figure out how many clusters, and then you go from there.
Not matrix. You can create the method, but what you have to do is you have to redo the method anyway, right? Once you get the range, right? Okay, this is the value of K that I'm thinking I might get, right? It might be anywhere from 5 to 15, let's say, right? Then what you do is you will rerun the model. You will have to rerun it. That's exactly what we did here, right? Where's my notebook? Okay, here it is. So see here, we did the model initially, right? Okay, where is it? Okay, here. So here we are doing the model, but when you are doing the Silhouette score or anything, you are redoing the model here again, right? Because every time you have to specify a new K value, rerun the model. So you are copying, pasting the same code inside a loop where you're changing the parameter value here every time with every loop. And in each iteration, it calculates a score, so stores it, and then you get this curve. Clear, Susan?
Yeah. Can you go up in the code?
Sure. This one here, or?
Yeah, so where you say cluster in range 2 to 11, is that the number of clusters where we want?
Yeah, you are iterating, right? So see here, right? K means n clusters is equals to n underscore cluster, right?
No, I was talking about range.
Range. Yeah. So this is where you are specifying that I want to know what's the Silhouette score for all cluster values starting from 2 to 10. So if my data has 2 clusters, what's my Silhouette score?
0
if my data
to 1.
has, exactly.
Oh, sorry.
So it will be between 0 to 1, correct? It will be between 0 to 1. But what exactly is that score? And how does it compare to when I have 3 clusters? How does it compare to when I have 4 clusters? How does it compare to when I have 5? So on, all the way up to 10. So I am rerunning the K-means model for all K values starting from 2 to 10. Make sense now?
Yes.
That's what the for loop is for. Rerunning the K-means model, because you don't know what's the optimal number, right? So at each number of K, you are calculating the Silhouette score. At the end of it, you compare all the Silhouette scores and see where the peak is, and that becomes your optimal number of clusters.
So the label now is like the range that is in the loop, right? Is that the
label? Yes. Okay, got it. Yeah, so this is the K will become the number of labels in your data set. That is correct, Jude. Okay. So when you say K equals to 2, your see, for example, in this case, right, we said K equals to 10. So the clustering algorithm is trying to come up with 10 labels, right? And it's trying to color these points based on these labels, right? Like it's saying that, okay, these are all points which are one cluster, this is another cluster, this is another one, this is another one, and so on. So this is the number of labels. So this here as well, right? Like you're saying, does my data have 2 labels or 10 labels or something in between? What's the best number of labels to have for my data set? Best number of groups, distinct groups. Okay. And the answer is five different labels for each of these 5 blobs here that we created. This is the perfect figure with minimum number of error in misclassifications, right? Because let's say if I say 10, so all of these were supposed to be one cluster, but what am I doing? I am misclassifying so many points. I'm misclassifying all these points. The reality is this, right? Whereas I'm trying to come up with this. So see how much error is there when you have 10 labels. You getting this, Jude?
Yeah.
But when you have 5, right? The labels correspond. Yeah. So the labels correspond to this real figure that I have. These are the real labels 0, 1, 2, 3, 4, right? This seems pretty close to the reality, pretty accurate. Save some points here, right? You know, which will be like, and some points on the corner here, which are closer, right? But this is pretty good. If I do 6 as well, right? It's not a pretty picture, right? All of these points are misclassified as a different cluster, whereas it's all part of one cluster. Awesome. All right, that's it for tonight, folks.